Imagine a world where your electric vehicle makes twice the journey on half the charge. Your devices last longer and process information quicker. Imagine a world where fighting diseases is faster, where life's experiences are brighter without taxing the earth. Imagine a world where crops are superior in quality, infinitely more valuable to our planet. Imagine a world where all of this was possible. The Coretec Group, engineering silicon to improve life.
Hi, my name is Ramez Elgammal. I'm the VP of Technology at the Coretec Group, and I'm here to talk to you today about routes to novel dielectric and semiconductor devices using cyclohexasilane. So some information about the Coretec Group. So we are a pioneer of new silicon-based products. So in addition to cyclohexasilane, we are in the process of manufacturing and evaluating a wide variety of silicon-based nanomaterials that can find applications in a wide variety of markets, including energy storage, electronics, semiconductor, solar, EVs, health, solid-state lighting, and agriculture. And so we've partnered with Evonik, a global leader in specialty chemicals, to manufacture CHS. And we're shipping samples to customers globally. So we've been collaborating extensively with different research institutions around the world to expand our IP portfolio that on new silicon-based materials that serve those markets above, as well as conversion of CHS to some unique silicon nanostructures. So our key product, cyclohexasilane, can alloy readily with germanium, boron, phosphorus, and a wide variety of other atoms, often with atomic percentages much higher than you would normally find with more conventional materials. It's a liquid at room temperature, and due to the structure of CHS, it has some unique chemistry, unique reactivities that result in higher deposition rates at lower temperature, especially when compared to more conventional precursors. So a wide variety of materials have been made with CHS, in addition to pure silicon and doped silicon, silicon nitride, silicon carbide, silicon oxide, thin films, nanoparticles, and even some nanowires. There's no need for me to talk extensively on why ALD is an important technique to fabricate semiconductor devices, but it's also well known that the next generation semiconductor devices will require low temperature deposition of silicon-based dielectric films, especially ones that require high aspect ratio nanostructures. And this is kind of a challenge, or has traditionally been a challenge to do, and we think that silicon derived from cyclohexasilane can help meet those needs. And as the the industry transitions from CVD to ALD, finding a suitable silicon precursor to make devices that require silicon nitride and silicon carbides has become a challenge, and we believe CHS will help address those challenges as well. So in cases where thermal budget is important, even transitioning to PECVD can be a challenge because those materials are often not conformal. So what's required of an ideal ALD precursor? So something that's at the intersection of having the right reactivity, the right volatility, and the right thermal stability. And so the intersection of those three is met by CHS. So more generally, these precursors should be liquids. So not only does that make transportation of them much more easy than than that of a gas, but during the deposition process, having a liquid precursor helps ensure that you have a constant evaporation due to the constant surface area in the vessel holding that liquid. Another requirement is that byproducts formed be volatile and ideally non-toxic. So CHS only gives one byproduct. It gives hydrogen is the byproduct. That the precursor is thermally stable and often for long periods of time, so ideally over a year. And that can be made in relatively few steps, so ideally 2 or less, and in a way that's scalable and also cost efficient. So we believe CHS also meets those other criteria as well. So taking a look at the physical properties, so CHS melts right below room temperature, so it's a liquid at room temperature. It boils at 226 degrees and relatively low at modest vacuum, so 10 torr. It boils at 80. When stored under inert atmosphere, we have strong evidence that it's stable for at least 18 months. And so CHS is made in 2 steps from inexpensive commodity chemicals such as trichlorosilane. And when CHS is converted to a silicon-based product on a mass basis, there's high atom economy, high yielding deposition because the only atoms that are in CHS, silicon and hydrogen. So by mass, silicon predominates the mass of the starting material. It also predominates the mass of the product. And we can see in that graph on the right that at room temperature, it has a relatively low vapor pressure, and at temperatures as low as 100 degrees, it's very well suited for delivery into an ALD reactor. So what's the origin of some of the chemistry of CHS? So we think it's due to a relatively low silicon-silicon and silicon-hydrogen bond dissociation energy, especially when compared to other perhydrodoxylanes. So part of this is due to the ring strain, relieving that ring strain when CHS is opened up and subsequently reacted or deposited onto a substrate. And so this lower bond dissociation energy, or BDE, gives rise to a lower deposition temperature as well as improved kinetics. And so as well as a more simple apparatus for delivery, which reduces CapEx, and a lower thermal budget, which reduces OpEx. So looking at perhydrodoxylanes that have been evaluated with ALD, so there are only a few examples. Here is one using neopentacylene and comparing that to trisilolamine to give rise to a silicon nitride film. So we see that even though the neopentacylane is reacted with the nitrogen plasma, so more of a bimolecular reaction, it still has at least a 10% higher growth rate than trisilolamine. And more generally, as the number of silicon atoms increases in a precursor, you expect to see an increase as that silicon count in the precursor increases. That bodes well for CHS. So highly conformal films of silicon nitride were generated with neopentacylane with relatively low hydrogen atom concentrations in the film, and the films were also of good quality as evidenced by the low wet etch rates. So how does CHS go to silicon or silicon-based product? Well, first, under heating or in the presence of of UV irradiation, ring opens to a polysilane, and then further heating converts that polysilane into an amorphous silicon. And that hydrogen content in the amorphous silicon derived from CHS is the lowest of all known per-hydrodoxylanes. And if you want an amorphous material, you could stop there, or you could heat to a higher temperature or anneal with a laser to give rise to a crystalline silicon. So CHS has been used in a variety of different deposition methods. So here we're looking at PECVD using CHS, and what we see is that the hydrogen content in the film, as I stated earlier, is much lower than what's typically seen with perhydrodoxylanes. So 3 to 5% is typical. You can go slightly lower with control over the chamber pressure and the flow rate as well. So there was a technique developed several years ago called aerosol-assisted CVD. And so here, liquid precursor is aerosolized at atmospheric pressure. And so cyclohexasilane, cyclopentacylane, and monosilane were compared here. And we see that the growth rates, so even at these low temperatures, are much higher with these cyclic silanes compared to monosilane. And this is primarily due to the low activation energy of deposition. So this method has been used to make both pure silicon, doped silicon, some silicon low-K dielectrics, silicon carbides, and silicon nitrides. So what types of materials are possible with CHS due to its unique reactivity? Well, everything you see here on the screen. So because CHS has ideal reaction chemistry, so it can readily make the standard dielectric materials, so silicon oxides, carbides, and nitrides, as well as ternary blends that are finding increased importance in semiconductor devices. And some of the unique chemistry that CHS gives rise to more challenging types of nitrides, carbides, and ternary materials due to the intrinsically greater resistance for diffusion migration. And so that unique chemistry helps address some of those barriers. So looking at silicon nitride, there's a recent paper that evaluated all the perhydrodoxylanes, so linear, branched, and cyclic silanes, and the results from the DFT calculation suggest that CHS is the best suited to form not just of the cyclic silanes, but of all the perhydrodoxylanes, silicon nitride by ALD. And then one other example of a perhydrodoxylane, neopentacylene, was examined here to make silicon carbides. And again, comparing neopentacylane to other linear silanes, it was shown to have the highest growth rate at the lowest temperatures. So we expect when CHS is evaluated that it'll perform even better. So wrapping up, so CHS once again has delivers 6 atoms of silicon per molecule, and our PECVD results suggest a lot of promise for ALD. High quality films can be grown. The relatively low vapor pressure makes it easier to transport and safer than gaseous silanes, and it doesn't require any dilution. We welcome questions and collaborations with the community, and thank you for your time.